Hi, Natchapan.
Hello. I hope you can hear me well.
Yes, I can hear you. I can
Awesome.
see you.
I can just go ahead and share already.
So you can share your screen if you want.
Entire screen, share. And there we go.
Great. And we'll wait for a few minutes for people to drop in, but please your setup.
Yeah. It looks to be doing okay.
John has come over to the light side again. So I gave some participation numbers yesterday. I think at the top we were 74 people in AirMeet, and I thought we were about 23 or so in YouTube. But according to Annalie, actually there were 100 people watching in YouTube the invited talk of yesterday. That is maximum. Which I think is very good. We're still working on making talks public after the symposium has taken place. But that's a bit more complicated in our case because we only have a live stream. We don't have pre-recorded videos.
It was quite convenient to not have to record videos.
Yeah, I thought so too. But
I mean, sure, there's a risk, but it's better than.
There are actually a few pre-recorded videos for people that did this just in case.
Recording takes an awful lot of time because it's hard to excuse yourself for the little mistakes that you make.
Yes, exactly. Yeah, or you have to do it as this. There was one talk at ICFP who had programmed his entire talk. So it was spoken by a robot voice, a female robot voice. It was Manuel Serrano. He had programmed it with his own JavaScript compiler.
Wow.
And the nice thing is that, she doesn't make mistakes. And he said it took him less time than actually having to prepare it by hand. And everything, of course, is completely synchronized with the text on the slides because it's completely programmed. The text and the slides are completely programmed in his case.
Right.
As one whole. I do think it's a bit harder to keep your attention with such a voice. Like. All right, it is now 1 o'clock, but let's give latecomers a bit of time to 1 minute or so, and then we really have to start. I will quickly make Richard co-host, just in case things go wrong again with the sound on my side. Welcome, Richard Burke, and thanks, Richard, and thanks again for helping out in case of disasters.
Yeah, no problem.
So we're a healthy 46 already. So I think we should just get started. People can hop in. Welcome everybody to the second day of the Haskell Symposium. The first talk, there will be 3 talks. Then we have a break. Then there's the invited talk by Jean-Philippe Bernardi on linear Haskell yet again, but now more from a technical scientific perspective. And afterwards, there were 2 more talks, including one on linear Haskell. So you might as well call this the linear Haskell Symposium, I guess. But we start off today with Natchapan, Daliapan. And I would say, okay, take it away.
Yeah, thank you. All right, so let me get started. All right, so you should be able to see my slides now. So welcome. This is a talk essentially about normalization for EDSLs, and this is joint work with Alejandro Russo, Sam Lindley, and I'm the other guy there. So like I said, this is a talk about EDSLs, right? So it's important that we take the perspective of an EDSL designer and put on our EDSL designer hats. So let us all do that. Right. So what we're looking at here is an EDSL, which takes the form of a deep embedding, right? And it's implemented using a data type, an expression data type. And here we have ways to insert integer literals. We have ways to add and multiply integer expressions. And most importantly, there's a variable constructor, which allows us to insert unknowns or free variables into this language, right? So this is important to the story. Just take note of that, right? Okay, so here's what we're going to do. So we're EDSL designers. We would like to extend this EDSL with arrays, right? So by arrays, I just mean like immutable full arrays as we know them. So, since we're dealing with deep embedding, we may go about them by extending our expression language with a few constructors, which denote the array operations we're interested in. So here we're going to add a way to construct new arrays, to compute the length of an array, and to index into an array. What the new array constructor takes, you compute the length of an array, you give it the length of an array and a function which, computes the elements or gives you the elements of the array, and you get an expression of an array type, a standard deep embedding way of going about things. Using this, you can derive a map array combinator using the standard array operations, which has the length of the original array, and you apply the function by indexing into the array. So this is a nice derived combinator, but it lacks properties of fusion, right? So if you consecutive map arrays are not fused, because all you're doing is simply building syntax, it's a little too much to expect fusion to happen out of the box. So in such cases, typically one resorts to a form of shallow embedding, where instead of extending your expression language with the necessary syntax, you say, oh, well, I can implement a notion of arrays in Haskell. Let me implement that in Haskell and piggyback on Haskell's way to deal with arrays to program arrays in my EDSL. How do you do that? Well, here's a data type similar to the new array constructor before, which takes an argument which denotes the length and a function as before and returns an array. And you can implement the array operations as before. Before there were constructors, now there are Haskell functions. Also has the same signature, but notice that the result, the types of the arguments are similar, but notice that the result is an array of an expression. That is an array containing an expression of type A, as opposed to an expression of an array type, right? So this is what I'm going to use to denote shallow embedding. And similarly, you can implement length of an array and index of an array by projecting out the arguments to the constructor, right? Once again, you can implement a map array using these functions, which, for the shallow embedding combinators, essentially. And here, unlike the previous case, you have fusion properties. Well, intuitively, all that's happening here is that we're leveraging Haskell's execution mechanism to achieve fusion in our shallow embedded arrays, right? And one can also observe this by essentially sort of inlining these functions, doing a bit of equation reasoning, and by observing that the left and the right-hand side are equal, and that there's no unnecessary intermediate arrays created, which is what all I mean by fusion here. Right, okay, but we've lost something in the process. There's no longer a syntactic representation of these array operations, right? So that was nice because we could generate code for array operations before, but now we cannot do them anymore because they're just Haskell functions. So, it's quite common to sort of retain the benefits of both by combining these representations by having a way of going back and forth, right? So you have 2EXP, which takes a shallow embedding, spits out the deep, and then you have from EXP, which goes backwards. And you also have a requirement that, composing them in this fashion as here must be equal to the identity. Now, using this sort of juggling back and forth, you can implement a combined embedding combinator, if you will, of a map array, which essentially, it takes the given array expression, converts it to the semantics first, applies mapping in the semantics, so it leverages fusion in the semantics, and then converts it finally back into syntax, right? So what's neat about this map array, however, is that you now have fusion in the syntax, right? That's quite neat because you didn't actually do any rewriting or any syntactic manipulation. Everything's was achieved in the semantics, and you managed to refi it back into syntax. This is quite nice, and it works really well, for example, for pairs of expressions and also for functions and expressions. So it's a rather neat trick, but it fails, however, for more complicated types which have multiple introduction forms. For example, integers or sums or exceptions. And why is that? Well, this is because It fails when you try to go back from a deep embedding to a shallow embedding. Well, this is because of unknowns, right? And why is that? So let's say I give you a variable x of the type exp_int, and I say, give me a shallow embedding representation, an integer, from this variable. How are we going to do that? There's multiple choices, so we cannot quite go back. So at this point, one may think, oh, well, but maybe the choice of shallow embedding is a problem. Can we sort of refine this shallow embedding and, somehow sort of keep track of how we can keep track of the expressions with unknowns in the semantics and somehow get away with that as well? You may as well. It may be possible to get away with it. But now the problem is we can no longer pretend that the shallow embedding is a sort of a natural semantic interpretation of the type that we're interested in, right? So we cannot reuse the host language features out of the box. You can't use addition and multiplication on integers as it is out of the box on your new semantic interpretation, for example. And also it's a bit mixed up, you're mixing up syntax and semantics, and it's a little bit difficult to reason about what exactly is going on. How do you prove the story correct? How do you know that the compiler, the EDSL compiler that you're writing, produces this semantically equivalent programs in spite of the fusion and the optimization that we're interested in? This is where it gets a bit complicated. But the main idea, the answer to this is essentially the essence of this paper, is to say, well, normalization by evaluation, or NBE, provides a principled account of specializing expression syntax by leveraging their semantics, right? And the key, so normalization by evaluation is a well-known technique, but the key here is the shift in perspective from deep embedding to syntax and from shallow embedding to semantics, right? And so that's essentially the idea that we're going to work with in the rest of this talk. Okay, so now when I say normalization, typically, at least in my mind, something like this comes up, right? I'm thinking, oh, well, you have some expressions, you're normalizing things, which is essentially by rewriting the syntax, and you end up in some kind of a specialized expression, which we're going to call normal forms. This is the traditional way of normalizing things. But NBE, on the other hand, has a deep involvement of semantics, right? So you start off with syntax, as always, and then you evaluate them into a suitable semantic domain, where you do the hard work by leveraging Haskell's or some other host language's evaluation mechanism, and then you reify the semantic value back into syntax, just as we did in the shallow embedding, deep embedding combination, and the result would be a specialized expression in normal form. NBE is a very similar story in that sense. It's just a more structured account of the story. Right, so the toolkit we're going to be dealing with, right? So here's a frame. By toolkit, I just mean a framework that we can instantiate and implement for our EDSLs. So here's a type class, RF or reifiable, and there's a type family which allows you to define a semantic domain which interprets the object language type that we're dealing with. But it's not just any semantic domain we're interested in. We want some additional structure on this domain, and this structure are these two operations, reify and reflect. Reify essentially takes a semantic value and converts it to a normal form, which is just a specialized expression. And reflect is NBE's solution, essentially, it's NBE's answer to deal with expressions with unknowns in them, right? And these expressions are also called as neutrals, are inductively characterized by a different data type called E. And reflect, the job of reflex is to insert these expressions with unknowns into the semantic domain defined by the type family. So the other major component is, once we've identified the suitable semantic domain, we have to write an evaluator or an interpreter which takes these expressions, evaluates them into the semantic domain, and then finally, once you've done that, you have a normalization function simply by composing eval and reify. So you evaluate and then you reify, and you end up with in a normal form just by observing the signatures, type signatures of these functions here. Right. So let's kind of take this framework for a spin and see, what it feels like in some sense. So let's look at integers, which are a bit of a problematic situation before. And for this purposes of this talk, let's just consider two simple equations that we're interested in. Those are that if we add two literals, we want the addition of those two literals. We want the result to be a literal. And if we multiply two literals, we want the multiplication to be literal as well. We want our normalizer to apply these equations whenever possible. And that's essentially what I mean by equations for NBE. And once we've identified those equations, it's the next natural thing to do here is to essentially look at define neutrals, right? So like I said, neutrals are essentially expressions with unknowns in them. But let's try to inductively characterize them. A variable is clearly an unknown. We cannot determine the value of it. But also you can have an addition where the first argument is unknown. So then, okay, you allow the first argument to be an unknown. You can have an addition where the second operand or the second argument is an unknown, or maybe both of them are unknown, right? So we don't know. It could be, for example, x plus y. In that case, that you would use the NAD constructor. And similarly, you would define constructors for multiplication as well. So the key idea here is neutrals inductively characterize what it means for expressions to be stuck at unknowns. That's the key thing about neutrals. But once we've identified them, then it's time to start thinking about what is the result that we want the normalizer to produce. Well, in our simple case, all we're saying is that we want the result of specializing an expression of an integer type to be an integer literal, meaning fully evaluated, or a neutral, which means you couldn't quite do everything, but just as much as well as you could do is what a neutral represents. So it's only one of these two possible values, and that's what a normal form reflects using the n-up and n-lift constructors. And once you've defined normal forms, then the semantic domain just kind of shows up in some sense, right? So because it just resembles the normal forms. And the semantic domain is defined similarly, where we say, well, we interpret integers as either expressions with unknowns in them, or neutrals of type integer, or their integer values, meaning fully specialized. And of course, we must also implement refi and reflect. Refi replaces the left injection by n-up, which is essentially taking the neutral and inserting it into normal forms. And refi replaces the right injection by n-lift, which is just a literal and normal form. Reflection, on the other hand, is just the left injection here. Remember, reflect inserts a neutral into semantics, and that's what the left injection does according to our semantic definition here. So that's the instantiation of the type class. What remains for us to do is to implement the evaluator for addition and multiplication. And the way we do that is we define a semantic addition function, which takes two semantic integers, and it returns a semantic integer. Now, a semantic integer is basically is of the either type, which means you can pattern match on it, and you can get a left or a right injection. And if both of them happen to be right injections, meaning they're literals, well, you can perform the addition that you're interested in. But if one of them is stuck, which meaning it's stuck at some unknown and you don't know what to do with it, you just build up a neutral and you reflect it into the semantics, right? Because you don't know what to do with it, you're just going to sort of say, oh, okay, I'm stuck, so here you go. Just reflect this back into the semantics. And we do the same thing for multiplication as well by pattern matching and all the possible combinations, and either performing the appropriate semantic action or reflecting the constructed neutral back into the semantics. I say back, but I just mean into the semantics. So that completes the entire story. And as a result, what we have is a normalizer which applies those two equations for NBE, for integer expressions. And so just to give you another taste just to sort of tie it back to what we started off with, which was arrays. So for arrays, we identified the equations as the following. That is, if we have an array expression, it can be uniquely identified by an equivalent expression, which is sort of the eta expanded version, which says any array expression must be of the form new r, with the length of the original array and which indexes into the array. So this is the eta. The first line denotes the eta rule, and the second two lines, the latter lines essentially denote the beta or the computational rules. So if you compute the length of a new array, which is just as good as projecting out the second argument, and the index of a new array as good as projecting out the second argument, the latter case it was the first argument. So once we've identified the equations, typically we would do the same. There's a recipe here, right? We would identify the neutrals and identify the normal forms, and then sort of do the semantic domain. So I'm going to skip ahead to the semantic domain directly, and only to show you that it resembles shallow embedding, because once again we have a semantic domain which is defined by a data type, which accepts a semantic integer in place of an expression of an integer type, and a function which gives you the elements of the array as before, and it returns a semantic array. New array, length array, index array, as in the case of shallow embedding, are implemented exactly the same way. You use the constructor to construct them, and you project out the arguments in case of the other functions, right? And once you have the semantic operations, all you have to do is sort of fill in the rest of the story. Well, we instantiate the type class so we interpret arrays by this new semantic array that we've defined. Refi essentially, does a bit of juggling between semantics and syntax. So it takes a semantic array, it constructs a syntactic array in normal form, and reflection receives a syntactic neutral. So essentially, it constructs a semantic array. It can be filled out. It's just a bit of sort of recursive application of things. Not a lot of intellectual complexity there, if you will. And then the last bit is, of course, to implement evaluation. And for evaluation, well, we've already defined in the previous slide, we had identified new array, length array, and index array operations in the semantics. So we use them to interpret the things in the syntax. And that once again completes NBE, but now for arrays. And so it's kind of systematic how we're going about doing these things, which is the nice thing about NBE. So you can also do this for the other types, for other more pure types, for functions, products, sum types. But you can also do this for computational effects, which is quite interesting, which means you can normalize effectful computations for exceptions and state effects. So the case for sums is a little bit complicated, so because it sort of messes with the other instances, it sort of pervades the implementation. But there's a more detailed account of how you can solve these problems, which arises due to the unruly eliminator of sum types in the paper, and how they sort of interact with effects in certain ways, and how you can go about solving them. That's in the paper. But instead of going through the full details of these instances, I'd much rather show you what it is that we get out of defining these instances at the end. What kind of examples, what kind of programs do we get at the end of the day? Right, so we're back to map fusion, but now I want to show you an example of a fusion in the presence of some kind of a pattern matching or branching in a program. So in this case, what we're essentially doing is we have a program which receives two arguments. One is of the either type and one is an array type. I'm going to call the first one a scrutiny and the second one an array. And what we're going to return essentially is an array, which is computed by the result of mapping with +1 or add 1 here. And all the things in blue here, just deep embedded combinators. Now we're only dealing with deep embedding, so that's the only kind of combinator that we're going to program with. And the array argument to this map arr over here is defined by pattern matching on the scrutiny argument. And on one branch you have another map operation, on the other branch you just have an array. The only thing that I'm trying to point out here, there's an opportunity for fusion on the first branch because there's two map operations, but on the second branch you must preserve the original map. So it's a slightly non-trivial interaction of how fusion should be done. And what you would expect, the result is also kind of expected. When you normalize this program in GHCI, what you get is a result. So let me walk you through the result. Essentially, this represents a function, the internal representation which is of this function, which is basically it receives two arguments and returns a single new array, which has the length of the original array, which was given as an argument, and the body of the array is computed by pattern matching. So essentially what's happened is that the case statement has been delayed to the point of absolute necessity. And on one branch, you can notice that it's the original array incremented with x and +1, which is basically the fusion of these two map operations, add 1 and add x. And in the second branch, you can notice that there's only a +1, and that's because of the original map has been preserved in the second branch. So essentially all the maps have been computed. There are no intermediate arrays. Notice that in the result, there's only one array which is being created. So that's kind of the result we get out of fusing array operations here. So that's nice, but you can also do a similar story for effects. So what you can do is, for example, in this program, you have an expression it's of a function type, which takes an array expression and it returns a stateful computation. Now let's look at this. It takes an array and then it says it's maps over the array with the +2, puts it, maps over to +1, puts that, and then gets the result and then returns the head of the array in the state. So, but the thing that we should notice here, there are two subsequent or two consecutive put operations. Clearly, the second one overwrites the first, so the first one can be thrown away, a put fusion. And then the get after the put is kind of useless because you know exactly what the state is, which is the array incremented with the 1. So this intermediate array is also a little bit useless. So we're trying to get rid of these in the result, and by minimizing the put and the gets in the result. We normalize this program and we get one get and one put. So the put operation here, you can see, is basically stores a new array where the array has been incremented. The values of the original array have been incremented by +1, which is expected because you want to throw away the first put. And what you return is essentially the result of what you had, the head of the result of what you had stored incremented by 1, which is the same as the head of the original array incremented by 1. And that's what you return. There is an unnecessary get here, but this is kind of the consequence of eta expansion, which is the next bit that I want to get into. Because at this point, you may also be wondering, what is so practical about this story? There's this blog post, I think, that Derek Dreyer has about any paper which has practical in its title is probably trying a little too hard. If I'm being honest, I think it's kind of true. We are trying a little bit hard, but that's only because NB is a good idea. I think EDSL developers, such as myself, should use it. Because it kind of gives you a nice refined account of what's going on. But really, by practical, what we mean here is that the standard approaches to NBE can lead to unnecessary expansions, as EJA expansion, because typically they're used in different more theoretical context. At least typed NB is used for things like equality checking and so on. So you want to adapt things a little bit for our purposes. So to illustrate a problem, let me show you this example. So let's say I normalize a variable array, which is of the type exp array of integers, right? And if I normalize this variable, what's going to happen is that I'm going to get an eta expanded form, which basically says, oh, well, the result of this normal form is a new array, which with the length is that of the original array and the index of, index into the original array, which is a bit wasteful, because if you normalize a variable, all you want is it's a variable, right? You don't want anything else to be done. And so, of course, you can solve this. That's kind of one of the things that I'm getting to, is you can do this by augmenting the semantics with a normal form, which doesn't, with a normal form, which represents reduced expressions which are not eta expanded. This is essentially, reflects a technique called gluing. So what we're doing here is we're gluing the semantics with the syntactic component, so that what happens during interpretation, we can sort of carefully build a piece of syntax that we would find we like, without actually leaving reification to the mercy of the semantics and having to reconstruct things, from scratch by eta expansion. As you can see here, Refi is a lot simpler now. You just sort of you project out the normal form, leaving all the work to the evaluation. So during evaluation, you will have to take care of this, which can be done if you do it the right way for defining normal forms. So of course, there's a lot more that I would like to tell you about, but it's all in the paper. So there's concerns about normalization, right? Because normalization causes duplication. We don't want that. So how do you? So there's a little story about how can you retain explicit sharing in the sort of semantic normalization process. How can you disable sharing, disable normalization on sub-expressions using a save combinator? There's concerns about, well, case expressions can explode. How do you optimize them? And sometimes you obviously want richer arithmetic equations. The equations that I showed you were very simplistic. You want, for example, to say that 0 plus x is equal to x. You want to say multiplication distributes over addition and so on. There's a number of other equations that one would like. This can also be found. And often you want to add domain-specific primitives that you don't really want to do much about, uninterpreted constants, such as fix, right? So because if you start normalizing fix, you're never going to terminate. So there are recipes to do this in the paper that you can have a look at if you'd like. So in a nutshell, here's essentially what I'm trying to say, sort of conclude things up, is that NDE provides a principled alternative to techniques that combine deep and shallow embedding for building and specializing EDSLs. There's a strong resemblance between both of these, but I think NB is a more systematic way of going about things. But what's also nice is the NB implementations are very modular. If you remember, our type class instances, they don't interfere with each other, and you can implement normalization for one, not for the other type, and so on. So you still have fine-grained control over the extent of specialization that you're interested in. Well, that brings me to the end of this talk. And if you'd like, well, obviously there's a paper on this matter, but you can also look at the GitHub link if you'd like to have a look at the code. Thanks.
Great, thank you very much. So there's a number of questions, and I will show the questions one by one on stage. The first is from Jesper Cox. Couldn't you just pick semint equals nf int?
Yes, you can.
Directly.
Sorry, maybe I was too quick. Yes, you can do that. The only reason to do that is because we want to sort of not, I mean, of course, it's more concise to do that directly, but I think this is basically to illustrate a point for, when you have sums, you start messing with the semantics a little bit more fine-grained way. But perhaps a more simpler answer that I'm trying to give away is that I still want to keep what's the syntax and semantics separate unless where it's absolutely necessary. If you put nf int, it just looks like a blob and you don't really know what it contains. And nf int could be defined as anything. I hope that.
Thanks a lot. I'll mark that as answered. The next one is by Gergo Erdi. Na2 can make progress given an exp into int. Why is it a neutral element?
Na2 can give right. So this is because right. So in the equations that I had picked, this wasn't supported. So it's because I had showed very simplistic equations. So in the actual implementation, if one can have a look at the code, so there's a slightly more sophisticated implementation where you actually get to deal with this, where you have a partial application and you want to specialize with respect to that. So it's only because of the equation that I've chosen for this presentation.
Mark that as answered. And then we have another question by Andrew Hirsch. Is there a reason for the choice of expint instead of semint in the semantics of arrays?
Yeah, that's just to avoid unnecessary. It could have been semint. That's a good spot. I mean, the question is, why is there a exp int on the function? I mean, that's because it's in a negative position. You can avoid some unnecessary work by making it exp int, but it could have been semint. It doesn't matter so much.
Okay, thanks. And then the final question at this point, at least, maybe other people get inspired to ask a few more questions. So Yousef Svenningsson asks, semantic domains can get very complicated. Do you have a story for making sure that they don't leak to the end user of the DSL so that they don't need to be confused by them?
Absolutely. So what's brilliant about the story is all of this is the compiler developer's problem, right? Because so the only thing that is exposed to the EDSL developer is the deep embedding. So of course now we're saying put everything into the expression syntax. So all you're going to do is construct the expression syntax. So the only complexity we're leaking, if you can call it that even, is how to construct ASTs. But no, the NBE story, regardless of whether it exists or it doesn't exist, none of that is carried over except for the restriction on the types, right? I mean, this is quite common for EDSLs to have sort of this type class restricting the type of the expression. So that's the only thing which kind of leaks. But apart from that, no, nothing else.
All right, thanks a lot. I'm gonna mark that as answered. Any other questions, or maybe some of the? Oh, wait a minute. There, I missed a few. John is asking a question as well. Is x times 0 neutral? If so, does that interact nicely with MBE, or do you effectively turn into a sum type as far as MBE is concerned?
So in the simplistic equations I showed, yes, x times 0 is a neutral, but of course that's a bit annoying. Like it's why would you want to generate code for x times 0? So in the sort of the claim I made about richer arithmetic equations, this equation is included as well. And no, this is a regex. It's not a neutral in the more sophisticated implementation. And so you have a choice depending on what equations you want. But for the latter, if so, does that interact nicely with MBE, or do you effectively turn int into a sum type as far as MBE is concerned? I'm missing something. I don't exactly follow the second part of the question, but maybe.
All right. What I will do, I will invite John to the stage, and then he can maybe specify more precisely what he means.
Yeah, that would be nice. Thank you.
I hope he's still there.
Well, but maybe I can quickly answer that. We don't do any turning int into a sum type. So maybe that answers the question already. We don't do that.
There's John.
Hello. Yes, so I was just wondering if you distinguish the 0 case from the non-zero case, does that effectively mean that you end up needing continuations as you do with when you have case expressions and sum types in MBE, or is everything just simple?
No, so it is a bit simpler. I mean, yes, you need a structure like we don't exactly use it's equivalent to the continuation. But there's a similar story. I don't know if that answers that.
Sorry, John, I muted you because I got feedback from your mic. But maybe you have to unmute it and then tell us whether you're satisfied or not.
Yeah.
I lost the sound, I'm afraid, but it's my setup, I think, which is causing the feedback. So just let's go on.
Okay. I'll mark this answer to remove you from the stage. And then we go to the final question. Because I think we have only time for a final question here. Yousef has another question for us. Do you have a story for incorporating heuristic optimizations as well, like a limited form of inlining or loop unrolling?
Right. So in the paper, there's something to do with. So there's a feed-based, sort of fuel-based, primitive recursion essentially. So there is a recursion story there. where you can control the amount of recursion because it's explicitly provided. Because you can do that, I can imagine that you can, I have no idea how this would be proved correct, but I can imagine implementing something in Haskell where you unroll a recursion combinator a certain number of times and you stop, because you do that already with a primitive recursion combinator. So yes, I haven't done it, but I can imagine. Yes, so I think that's your answer.
Okay. Well, let's thank the speaker again for his talk and answers. And I'm going to kindly uninvite him from the stage. And then I'll get